Now this is a continuation from the last video. The system is connected to the 28-volt DC electrical power supplied supplied from the aircraft. Alarm output and sensor sensitive checks are performed simply with the test switch on the control panel. Flame detectors. Optical sensors, often referred to as flame detectors, are designed to alarm when they detect the presence of prominent specific radiation emissions from hydrocarbon flames. The two types of optical sensors available are infrared IR and ultraviolet UV, based on the specific emission wavelengths that they are designed to detect. IR-based optical flame detectors are used primarily on light turboprop aircraft and helicopter engines. These sensors have proven to be very dependable and economical for these applications. When radiation emitted by the fire crosses the airspace between the fire and the detector, it impinges on the detector front face and window. The window allows a broad spectrum of radiation to pass into the detector where it strikes the sensing device filter. The filter allows only radiation in a tight wave band centered on 4.3 micrometers in the IR band to pass on to the radiation sensitive surface of the sensing device. The radiation striking the sensing device minutely raises its temperature, causing small thermoelectric voltages to be generated. These voltages are fed to an amplifier whose output is connected to various analytical electronic processing circuits. The processing electronics are tailored exactly to the time signature of all known hydrocarbon flame sources and ignores false alarm sources such as incandescent lights and sunlight. Alarm sensitivity level is accurately controlled by a digital circuit. Carbon monoxide detectors. Carbon monoxide is a colorless, odorless gas that is a byproduct of incomplete combustion. Its presence in the breathing air of human beings can be deadly to ensure crew and passenger safety. Carbon monoxide detectors are used in aircraft cabins and cockpits. They are most often found on reciprocating engine aircraft with exhaust shroud heaters and on aircraft equipped with a combustion heater. Turbine bleed air when used for heating the cabin is tapped off of the engine upstream of the combustion chamber. Therefore, no threat of carbon monoxide presence is posed. Carbon monoxide gas is found in varying degrees in all smoke and fumes of burning carbonaceous substances. Exceedingly small amounts of the gas are dangerous if inhaled. A, a concentration of as little as 2 parts in 10,000 may produce headache, mental dullness, and physical lethargy within a few hours. Prolonged exposure at higher concentrations may cause death. There are several types of carbon monoxide detectors. Electronic detectors are common, some are panel mounted, and others are portable. Chemical color change types are also common. These are mostly portable. Some are simple buttons, cards, or badges that have a chemical applied to the surface. Normally, the color of the chemical is tan. In the presence of carbon monoxide, the chemical darkens to gray or even black. This transition time required to change color is inversely related to the concentration of CO present. At 50 parts per million, the indication is apparent within 15 to 30 minutes. A concentration of 100 parts per million changes the color of the chemical in as little as 2 to 5 minutes. As concentration increases or duration of exposure is prolonged, the color evolves from gray to dark gray to black. If contaminated, installing a new indicating element allows a carbon monoxide portable test unit to be returned to service. Extinguishing agents and portable fire extinguishers. There must be at least one handheld portable fire extinguisher for use in the pilot compartment that is located within easy access of the pilot while seated. There must be at least one handheld fire extinguisher located conveniently in the passenger compartment of each airplane accommodating more than 6 and less than 30 passengers. Each extinguisher for use in a personal compartment must be designed to minimize the hazard of toxic gas concentrations. The number of portable handheld fire extinguishers for transport aircraft is shown in the next figure. halogenated hydrocarbons. For over 45 years, halogenated hydrocarbons, halons, have been practically the only fire extinguishing agents used in civil transport aircraft. However, halon is an ozone depleting and global warming chemical, and its production has been banned by international agreement. Although halon usage has been banned in some parts of the world, aviation has been granted an exemption because of its unique operational and fire system requirements. Halon has been the fire extinguishing agent of choice in civil aviation because it is extremely effective on a per unit weight basis over a wide range of aircraft environmental conditions. It is a clean agent, no residue, electrically non-conducting, and has relatively low toxicity. Two types of halons are employed in aviation. Halon 1301 CBR F3, a total flooding agent, and Halon 1211 CBR CIF2, a streaming agent. Class A, B, or C fires are appropriately controlled with halons. However, do not use halons on a Class D fire. Halon agents may react vigorously with the burning metal. While halons are still in service and are appropriate agents for these classes of fire, the production of these ozone depleting agents has been restricted. Although not required, consider replacing halon extinguishers with halon replacement extinguishers when discharged. Halon replacement agents found to be compliant to date include the halocarbons HCFC Blend B, HFC 227EA, and HFC 236FA. Inert cold gases. Carbon dioxide, CO2, is an effective extinguishing agent. It is most often used in fire extinguishers that are available on the ramp to fight fires on the exterior of the aircraft, such as engine or APU fires. CO2 has been used for many years to extinguish flammable fluid fires and fires involving electrical equipment. It is non combustible and does not react with most substances. It provides its own pressure for discharge from the storage vessel, except in extremely cold climates where a booster charge of nitrogen may be added to winterize the system. Normally, CO2 is a gas, but it is easily liquefied by compression and cooling. After liquefaction, CO2 remains in a closed container as both liquid and gas. When CO2 is then discharged to the atmosphere, most of the liquid expands to gas. Heat absorbed Heat absorbed by the gas during vaporization cools the remaining liquids to negative 110 degrees Fahrenheit, and it becomes a finely divided white solid dry ice snow. Carbon dioxide is about 1.5 times as heavy as air, which gives it the ability to replace air above burning surfaces and maintain a smothering atmosphere. CO2 CO2 is considered only mildly toxic, but it can cause unconsciousness and death by suffocation if the system is allowed to breathe CO2 in fire extinguishing concentrations for 20 to 30 minutes. CO2 effective as an is not effective as an extinguishing agent on fires involving chemicals containing their own oxygen supply, such as cellulose nitrate used in some aircraft paints. Also, fires involving magnesium and titanium cannot be extinguished by CO2. Dry powders. Class A, B, or C fires can be controlled by dry chemical extinguishing agents. The only all-purpose Class A, B, C rating dry chemical powder extinguishers contain monoammonium phosphate. All other dry chemical powders have a Class B, C, US, UL fire rating only. Dry powder chemical extinguishers best control Class A, B, and C fire, but their use is limited due to residual residue and cleanup after deployment. Class A type fires are best controlled with water by cooling the material below its ignition temperature and soaking the material to prevent reignition. Cockpit and cabin interiors. All materials used in the cockpit and cabin must conform to strict standards to prevent fire. In case of a fire, several types of portable fire extinguishers are available to fight the fire. The most common types are Halon 1211 and water. Extinguisher types. Portable fire extinguishers are used to extinguish fires in the cabin or flight deck. The halon extinguishers are used on electrical and flammable liquid fires. Some transport aircraft also use water fire extinguisher for use on non-electrical fires. The following is a list of extinguishing agents and the type class fires for which each is appropriate. 1. Water. Class A. A water cools the materials below its ignition temperature and soaks it to prevent reignition. 2. Carbon dioxide. Class B or C. CO2 acts as a blanketing agent. Note, CO2 is not recommended for handheld extinguishers for internal aircraft use. 3. Dry chemicals. Class A, B, or C. Dry chemicals are the best control agents for these type of fires. Halons, only class A, B, or C. Halocarbon clean agents, only class A, B, or C. Specialized dry powder. Class D. Follow the recommendations of the extinguisher's manufacturer because of the possible chemical reaction between the burning metal and the extinguishing agent. The following handheld extinguishers are unsuitable as cabin or cockpit equipment. CO2 dry chemicals due to the potential for corrosion damage to electronic equipment, the possibility of visual obstruction if the agent were discharged into the flight deck area, and the cleanup problems from their use. Specialized dry powder. It is suitable for use in ground operations. Installed fire extinguishing systems. Transport aircraft have fixed fire extinguishing systems installed in turbo engine compartments, APU compartments, cargo and baggage compartments, and lavatories. CO2 fire extinguishing systems. Older aircraft with reciprocating engines use CO2 as an extinguishing agent, but all newer aircraft designs with turbine engines use halon or equivalent extinguishing agent, such as halocarbon clean agents. Halogenated hydrocarbons fire extinguishing systems. The fixed fire extinguisher systems used in most engine fire and cargo compartment fire protection systems are designed to dilute the atmosphere with an inert agent that does not support combustion. Many systems use perforated tubing or discharge nozzles to distribute the extinguishing agent. High rate of discharge systems use open-end tubes to deliver a quantity of extinguishing agent in 1 to 2 seconds. The most common extinguishing agent still used today is Halon 1301 because of its effective firefighting capability and relatively low toxicity, UL classification group 6. Non-corrosive Halon 1301 does not affect the material it contacts and requires no cleanup when discharged. Halon 1301 is the current extinguishing agent for commercial aircraft, but a replacement is under development. Halon 1301 cannot be produced anymore because it depletes the ozone layer. Halon 1301 will be used until a suitable replacement is developed. Some military aircraft use HCl 125, and the Federal Aviation Administration (FAA) is testing HCl 125 for use in commercial aircraft. Containers. Fire extinguishing containers (HRD bottles) store a liquid halogenated extinguishing agent and pressurized gas, typically nitrogen. They are normally manufactured from stainless steel. Depending upon design considerations, alternate materials are available, including titanium. Containers are also available in a wide range of capacities. Containers are also available. They are produced under Department of Transportation (DOT) specifications for exemptions. Most aircraft containers are spherical in design, which provides the lightest weight possible. However, cylindrical shapes are available where space limitations are a factor. Each container incorporates a temperature/pressure sensitive safety relief diagram that prevents container pressure from exceeding container test pressure in the event of exposure to excessive temperatures. Discharge valves. Discharge valves are installed on the containers. A cartridge squib, a A frangible disc type valve are installed in the outlet of the discharge valve assembly. Special assemblies having solenoid operated or manually operated seat type valves are also available. Two types of cartridge disc release techniques are used. Standard release type uses a slug driven by explosive energy to rupture a segmented closure disc. For high temperature or hermetically sealed units, a direct explosive impact type cartridge is used that applies fragmentation impact to rupture a, a prestressed corrosion resistant steel diagram. Most containers are conventional metallic gasket seals that feature refurbishment following discharge. Pressure indication. A wide range of diagnostics is utilized to verify the fire extinguisher agent charge status. A simple visual indication gauge is available, typically a helical burden type indicator that is vibration resistant. A combustion gauge system switch a combustion gauge switch visually indicates actual container pressure and also provides an electrical signal if container pressure is lost, precluding the need for discharge indicators. A ground a ground checkable diagram type low pressure switch is commonly used on hermetically sealed containers. The KID system has a temperature compen- compensated pressure switch that tracks the container pressure variations with temperatures by using a hermetically sealed reference chamber. Two-way check valve. Two-way check valves are required in a two-shot system to prevent the extinguisher agent from a reserve container from backing up into the previous emptied main container. Valves are supplied with either MS33514 or MS33656 fitting configurations. Discharge indicator. Discharge indicators provide immediate visual evidence of container discharge on fire extinguishing agents. Two kinds of indicators can be furnished: thermal and discharge. Both types are designed for aircraft and skin mounting. Thermal discharge indicator. The thermal discharge indicator is connected to the fire container relief fitting and ejects a red disc to show when container contents have been dumped overboard due to excessive heat. The agent discharges through the opening left when the disc blows out. This gives the flight and maintenance crews an indication that the fire extinguishing container needs to be replaced before the next flight. Yellow disc discharge indicator. If the flight crew activates the fire extinguisher system, a yellow disc is ejected from the skin of the aircraft fuselage. This is an indication for the maintenance crew that the fire extinguishing system was activated by the flight crew and the fire extinguishing container needs to be replaced before next flight. Fire switch. The engine and APU fire switches are typically installed on the center overhead panel or center console on the flight deck. When an engine fire switch is activated, the following happens. The engine stops because the fuel control shuts off. The engine is isolated from the aircraft system and the fire extinguishing system is activated. Some aircraft use fire switches that need to be pulled and turned to activate the system, while others use a push type switch with a guard. To prevent accidental activation of the fire switch, a lock is installed that releases the fire switch only when a fire has been detected. This lock can be manually released by the flight crew if the fire detection system malfunctions. Cargo fire detection. Transport aircraft needs to have the following provisions for each cargo or baggage compartment. The detection system must provide a visual indication to the flight crew within 1 minute after the start of a fire. The system must be capable of detecting a fire at a temperature significantly below that at which the structural integrity of the airplane is substantially decreased. There must be means to allow the crew to check in flight the functioning of each fire detector circuit. Cargo compartment classification. Class A. A Class A cargo or baggage compartment is one in which the presence of a fire will be easily discovered by a crew member while at his or her station, and each part of the compartment is easily accessible in flight. Class B. A Class B cargo or baggage compartment is one in which there is sufficient access in flight to enable a crew member to effectively reach any part of the compartment with the contents of a hand fire extinguisher. When the access provisions are being used, no hazardous quantity of smoke, flames, or extinguishing agents enters any compartment occupied by the crew or passengers. There is a separate approved smoke detector or fire detector system to give warning at the pilot or flight engineer station. Class C. A Class C cargo or baggage compartment is one not meeting the requirements for either a Class A or B compartment, but in which there is a separate approved smoke detector or fire detector system to give warning at the pilot or flight engineer station. There is an approved built-in fire extinguishing or suppression system controlled from the cockpit. 3. There are means to exclude hazardous quantities of smoke, flames, or extinguishing agent from any compartment occupied by the crew or passengers. 4. There are means to control ventilation and drafts within the compartment so that the extinguishing agent used can control any fire that may start within the compartment. Class E. Class E cargo compartment is one on airplanes used only for the carriage of cargo and in which there is a separate approved smoke and fire detector system to give warning at the pilot or flight engineer station. The controls for shutting off the ventilating airflow to or within the compartment are accessible to the flight crew in the crew compartment. There are means to exclude hazardous quantities of smoke, flames, or noxious gas from the flight crew compartment. The required crew emergency exits are accessible under any cargo loading condition. Cargo and baggage compartment fire detection and extinguisher system. The cargo compartment smoke detection system gives warning in the flight deck if there is smoke in a cargo compartment. Each compartment is equipped with a smoke detector. The smoke detectors monitor air in the cargo compartments for smoke. The fans bring air from the cargo compartment into the smoke detector. Before the air goes in the smoke detector, inline water separators remove condensation and heaters increase the air temperature. Smoke detector system. The optical smoke detector consists of source light emitting diodes, LEDs, intensity monitor photodiodes, and scatter detector photodiodes. Inside the smoke detection chamber, airflow between a source LED and a scatter detector photodiode. Usually only a small amount of light from the LED gets to the scatter detector. If the air has smoke in it, the smoke particles reflect more light on the scatter detector. This causes an alarm signal. The intensity monitor photodiode makes sure that the source LED is on and keeps the output of the source LED constant. This configuration also finds contamination of the LED and photodiodes. A defective diode or contamination causes the detector to change the other set of diodes. The detector sends a fault message. The smoke detector has multiple sampling ports. The fans draw air from the sampling ports through a water separator and a heater unit to the smoke detector. Cargo compartment extinguishing system. The cargo compartment extinguishing system is activated by the flight crew if the smoke detectors detect smoke in the cargo compartment. Some aircraft are outfitted with two types of fire extinguisher containers. The first system is the dump system that releases the extinguishing agent directly when the cargo fire discharge switch is activated. This action extinguishes the fire. The second system is the metered system. After a time delay, the metered bottles discharge slowly and at a controlled rate through the filter regulator. Halon from the metered bottles replaces the extinguishing agent leakage. This keeps the correct concentration of extinguishing agent in the cargo compartment to keep the fire extinguished for 180 minutes. The fire extinguishing bottles contain Halon 1301 or equivalent fire extinguishing agent pressurized with nitrogen. Tubing connects the bottles to discharge nozzles in the cargo compartment ceilings. The extinguishing bottles are outfitted with squibs. The squib is an electrically operated explosive device. It is adjacent to a bottle diaphragm that can break. The diaphragm normally seals the pressurized bottle. When the cargo discharge switch is activated, the squib fires and the explosion breaks the diaphragm. Nitrogen pressure inside the bottle pushes the halon through the discharge port into the cargo compartment. When the bottle discharges, a pressure switch is activated that sends an indication to the flight deck that the bottle has been discharged. Flow control valves are incorporated if the bottle can be discharged in multiple compartments. The flow control valves direct the extinguishing agent to the selected cargo compartment. The following indications occur in the cockpit if there is smoke in a cargo compartment. Master warning lights come on. Fire warning oral operates. A cargo fire warning message shows. Cargo fire warning lights come on. The master warning lights and fire warning oral are prevented from operating during part of the takeoff operation. Lavatory smoke detectors. Airplanes that have a passenger capacity of 20 or more equipped with a smoke detector system that monitors the lavatories for smoke. Smoke indications provide a warning light in the cockpit or provide a warning light or audible warning at the lavatory and at flight attendant stations that would be readily detected by a flight attendant. Each lavatory must have a built-in fire extinguisher that discharges automatically. The smoke detector is located in the ceiling of the lavatory. Lavatory smoke detector system. The lavatory smoke detector is powered by the 28-volt DC left-right main DC bus. If there is smoke in the sensing chamber of the smoke detector, the alarm LED red comes on. The timing circuit makes an intermittent ground. The warning horn and lavatory call light operate intermittently. The smoke detection circuit makes a ground for the relay. The energized relay makes a ground signal for the overhead electronic unit OEU in the central monitoring system CMS. This interface gives these indications: lavatory master call light flashes, cabin system control panel CSCP, and cabin area control panel CACP pop-up window shows, and the lavatory call chime operates. Push the lavatory call reset switch or the smoke detector interrupt switch to cancel the smoke indications. If there is still smoke in the lavatory, the alarm LED stays on. All smoke indications go away automatically when the smoke is gone. Lavatory fire extinguisher system. The lavatory compartment is outfitted with a fire extinguisher bottle to extinguish fires in the waste compartment. The fire extinguisher is a bottle with two nozzles. The bottle contains pressurized halon 1301 or equivalent fire extinguishing agent. When the temperature in the waste compartment reaches approximately 170 degrees Fahrenheit, the solder that seals the nozzles melt and the halon is discharged. Weighing the bottle is often the only way to determine if the bottle is empty or full. Fire detection system maintenance. Fire detector sensing elements are located in many high activity areas around aircraft engines. Their location together with their small size increases the chance of damage to the sensing elements during maintenance. General maintenance of a fire detection system typically includes the inspection and servicing of damaged sections, containment of loose material that could short detector terminals, correcting connection joints and shielding, and replacement of damaged sensing elements. An inspection and maintenance program for all types of continuous loop systems should include the following visual checks. Note, these procedures are examples and should not be used to replace the applicable manufacturer's instructions. Sensing elements of a continuous loop system should be inspected for the following: cracked or broken sections caused by crushing or squeezing between inspection plates, cowl panels, or engine components, abrasion caused by rubbing of the element on cowling accessories or structural members, pieces of safety wire, other material particles that may short the spot detector terminals, condition of rubber grommets and mounting clamps that may be softened from exposure to oils or hardened from excessive heat, dents and kinks in sensing element sections, limits on the element diameter, acceptable dents and kinks and degree of smoothness of tubing contour are specified by manufacturers. No attempt should be made to straighten any acceptable dent or kink, since stresses may set up that could cause tubing failure. Nuts at the end of the sensing element should be inspected for tightness and safety wire. Loose nuts should be retorqued to the value specified by the manufacturer's instructions. Some types of sensing element connection joints require the use of copper crush gaskets. These should be replaced any time a connection is separated. If shielded flexible leads are used, this should be inspected for fraying of the outer braid. The braided sheath is made of many fine metal strands woven into a protection covering surrounding the inner insulated wire. Continuous bending of the cable or rough treatment can break these fine wires, especially those near the connectors. Sensing element routing and clamping should be inspected carefully. Long, unsupported sections may permit excessive vibration that can cause breakage. The distance between clamps on straight runs, usually about 8 to 10 inches, is specified by each manufacturer. In connectors, the first support clamp usually is located about 4 to 6 inches from the end connector fittings. In most cases, a straight run of 1 inch is maintained from all connectors before a bend is started, and an optimum bend radius of 3 inches is normally adhered to. Interference between a cowl brace and a sensing element can cause rubbing. This interference may cause wear and short the sensing element. Grommets should be installed on the sensing element so that both ends are centered on its clamp. The split end of the grommet should face the outside of the nearest bend. Clamps and grommets should fit the element snugly. Fire detection system troubleshooting. The following troubleshooting procedures present the most common difficulties encountered in engine fire detection systems. Intermittent alarms are most often caused by an intermittent short in the detector system wiring. Such shorts may be caused by a loose wire that occasionally touches a nearby terminal, a frayed wire brushing against a structure, or a sensing element rubbing against a structural member long enough to wear through the insulation. Intermittent faults often can be located by moving wires to recreate the short. Fire alarms and warning lights can occur when no engine fire overheat condition exists. Such false alarms can most easily located by disconnecting the engine sensing loop connections from the control unit. If the false alarm ceases when the engine sensing loop is disconnected, the fault is the disconnected sensing loop, which should be examined for areas that have been bent into contact with hot parts of the engine. If no bent element can be found, the shorted section can be located by isolating the connected elements consecutively around the entire loop. Kinks and sharp bends in the sensing element can cause an internal wire to short intermittently to the outer tubing. The fault can be located by checking the sensing element with an ohm meter while tapping the element in the suspected areas to produce the short. Moisture in the detection system seldom causes a false fire alarm. If, however, moisture does cause an alarm, the warning persists until the contamination is removed or boils away and the resistance of the loop returns to its normal value. Failure to obtain an alarm signal when the test switch is actuated may be caused by a defective test switch or control unit, the lack of electrical power, inoperative indicator light, or an opening in the sensing element or connecting wiring. When the test switch fails to provide an alarm, the continuity of a two-wire sensing loop can be determined by opening the loop and measuring the resistance. In a single-wire continuous loop system, the center conductor should be grounded. Fire extinguisher system maintenance. Regular maintenance of fire extinguisher systems typically includes such items as the inspection and servicing of fire extinguisher bottles, containers, removal and reinstallation of cartridges and discharge valves, testing of discharge tubing for leakage and electrical wiring continuity tests. The following paragraphs contain details of some of the most typical maintenance procedures. Container pressure check. Fire extinguisher containers are checked periodically to determine that the pressure is between the prescribed minimum and maximum limits. Changes of pressure with ambient temperatures must also fall within prescribed limits. The graph shown is typical of the pressure temperature curve graphs that provide maximum and minimum gauge readings. If the pressure does not fall within the graph limits, the extinguisher container is replaced. Discharge cartridges. The service life of fire extinguisher discharge cartridges is calculated from the manufacturer's date stamp, which is usually placed on the face of the cartridge. The cartridge service recommended by the manufacturer is usually in the terms of years. Cartridges are available with a service life of 5 years or more. To determine the unexpired service life of a discharge cartridge, it is usually necessary to remove the electrical leads and discharge line from the plug body, which can then be removed from the extinguisher container. Agent containers. Care must be taken in the replacement of cartridge and discharge valves. Most new extinguisher containers are supplied with their cartridge and discharge valves disassembled. Before installation on the aircraft, the cartridge must be assembled properly in the discharge valve and the valve connected to the container, usually by means of a swivel nut that tightens against the packing ring gasket. If a cartridge is removed from a discharge valve for any reason, it should not be used in another discharge valve assembly since the distance the contact point protrudes may vary with each unit. Thus, continuity might not exist if a used plug that had been indented with a long contact point were installed in a discharge valve with a shorter contact point. The preceding material in this chapter has been largely of a general nature, dealing with the principles involved and general procedures to be followed. When actually performing maintenance, always refer to the applicable maintenance manuals and the other related publications pertaining to a particular aircraft. Fire prevention. Leaking fuel, hydraulic dicing, or lubricating fluids can be sources of fire in an aircraft. The condition should be noted and corrective action taken when inspecting aircraft systems. Minute pressure leaks of these fluids are particularly dangerous for they quickly produce an explosive atmospheric condition. Carefully inspect fuel tank installations for signs of external leaks. With integral fuel tanks, the external evidence may occur at some distance from where the fuel is actually escaping. Many hydraulic fluids are flammable and should not be permitted to accumulate in the structure. Soundproofing and lagging materials may become highly flammable if soaked with oil of any kind. Any leakage or spillage of flammable fluid in the vicinity of combustion heaters is a serious fire risk, particularly if any vapor is drawn into the heater and passes over the hot combustion chamber. Oxygen system equipment must be kept absolutely free from traces of oil or grease since these substances spontaneously ignite when in contact with oxygen under pressure. Oxygen servicing cylinders should be clearly marked so they cannot be mistaken for cylinders containing air or nitrogen, as explosions have resulted from this error during maintenance operations. And that is the end of the fire protection system.